So thanks for having me to talk to your group. I should say right away, I am not a type theorist. I'm just a humble working programmer. And this is just stuff a lot of, so we started off from some well-established stuff and evolved it to meet our needs in various more or less crazy ways. So it'll be interesting to see how much your mouths drop when you see some of the stuff we've done, how crazy it is. Anyway, let's get on with it. Now I need to put, okay. Okay, so I think it's helpful just to have a little bit of background about where Ballerina is coming from. And WSO2 is a company that does open source enterprise integration. And the classic sort of technology in that world is called the Enterprise Service Bus, ESB. And if you look at it from a programming language point of view, what it is it's an XML sort of vocabulary, XML DSL basically, which has abstractions relating to network services, providing network services, routing stuff. And then ESB products typically have a graphical editor that allow you to edit that DSL. And that DSL gets, does the real heavy lifting is done by Java, components written in Java, which the DSL composes. So typically when you're writing real sophisticated applications, you're writing a bunch of, a pile of XML via the graphical editor, and then you're doing some stuff in Java. And the way this works commercially is you sell people a per server license of, X tens of thousands of dollars per server or whatever. And this whole model, it's, you have a server, you configure it, you write a bunch of XML and a bunch of Java. It's just not a great fit for the way the world's going. And so the concept behind Ballerina is, okay, maybe we can do this whole thing better by just having a programming language that does it all. So, a real programming language. So one of the problems with the Java XML combo is the XML stuff is not a real programming language. It doesn't have all the nice things that a programming language has for scaling up, in terms of modularity, abstractions, all that sort of thing. So you want a proper programming language with everything you kind of expect of a modern programming language. Batteries included, so all the things that you expect in a modern programming language: libraries, package manager, build system, test system, documentation system, IDE support, all that sort of stuff. It's stuff you really need to have in any credible language. Design it from the start to work in the cloud, and design it be something that's easy for programmers that are familiar with the well-known languages, widely used languages in the C family to get started with. And the initial implementation is based on Java. It compiles to JVM bytecodes. But one of the key ideas is that this is not a JVM language. We're not embracing the JVM. The fact that it's a JVM language is, for the most part, not exposed to the programmer. You can do Java integration if you want to, but the goal is that we can run other things, and we're working on that. So that's the concept. I think one thing that makes an enormous difference to the design is the being familiar bit. So all sorts of cool stuff that we might want to do is just a non-starter, because we want people who know JavaScript or TypeScript or something just to be able to get started and feel right at home immediately. So that's a big constraint on what we can do. So let me talk a little about, making a big language like this costs money, and somebody has to pay for it. And it's been developed by WSO2, which is, you've probably never heard of it, but it's actually it's a medium-sized company, been around for 15 years, got about 850 people in total probably. Engineering's mostly out of Sri Lanka. And we do enterprise integration, open source. And the concept is that Ballerina, the language, is free. So we're not trying to make money out of that. I don't think you can get any traction on a language that is proprietary these days. And it's free, including all the batteries included stuff I talked about, IDE, documentation, testing, all that sort of stuff. And the way one makes money off it is we have a cloud service called Choreo that builds on top of it that you can use for extra value-added stuff, and we get enterprises to pay us lots of money to use. And this is a long-term thing, so it's been going on. I don't know how long. I got involved maybe 3 years ago. It had been going for quite a few years before that, and it will be keeping. We're by no means done. So it's a long-term thing. So what are we trying to achieve? So today I'm not talking about Ballerina in general. I'm just going to focus on the type system. So what are we trying to achieve with the type system? Well, we're trying to do what a regular type system does. We want to describe the types of variables and functions used within the program. And our familiarity goal requires that we support mutation in a similar way to Java or JavaScript. So we can't have kind of ML style notation where it's explicit. You just basically want to mutate things pretty freely in the same way you do in Java and JavaScript. Where we're different is that we want the type system not only to be able to describe data that is being manipulated by the program, but we want it to be used to describe the data that network services send and receive. So we want it from, you just describe the types of your network services using the type system, and from that you can use it, you can derive the network interface. So you can derive GraphQL or Open API schema from the types. And in particular, we want a good fit with Json. Another important constraint is that we can't get too complicated. The kind of programs that we're trying to write, the kind of programs we're aiming at for people to write are not huge programs. We're not aiming for million-line programs. We're aiming for people who want to write. It's somewhere between on the scripting to systems programming spectrum. It's somewhere between a script, somewhere between the script and application end of the spectrum. And we're not trying to write one-line programs, but a lot of programs will be quite small programs, 100 lines, 200 lines, 1,000 lines, something like that. And this may not be the only programming language people are using. So we can't have a super complex type system that requires people to invest months and months learning it in order to be able to write programs. The type system has got to, we want to be able to scale up to do medium-sized programs, tens of thousands of lines. But the type system can't, it's not typing to the max. It's typing as much as actually really helps the net win. It's got to be a net win for the programmer. The amount the programmer invests in learning the type system has got to be paid back in making life easier for the programmer. So if there's one sort of big idea in the type system, or it's semantic subtyping, which is not a novel idea. It's I guess XJuice is the language that it's most well known for, and that's been taken further by CJuice. And we have one, Adrian was saying you like going through obscure papers. We have one obscure paper that we've heavily built on by a guy called Costagna in France, which explains how to do semantic subtyping. And the idea of semantic subtyping is that types denote sets of values, and that the subtyping relationship on types is defined by the subset relationships on the types they denote. So you don't have axioms saying, it's not based on the syntactic structure of the type, but it's based on the set of values that the type denotes. And that works. So why do we do this? Well, it works particularly well for describing tree structured data like JSON. It works well as a schema language. And it's just the right, I personally, I like it. I think it's the right thing to do. It gives a very nice, simple model. But it's not widely used. It's not widely used, and it has some implementation challenges. It's kind of like structural typing. I mean, it's related to structural typing in that typically goes hand in hand with structural typing, but it's not the same thing. You can have structural typing, but have syntactic rules for how you define subtypes. The nice thing about this is, you don't have to learn all the rules about the programmer, just has to have a model where, what we're trying to achieve is that the programmer has a model where they can just think of type instead of values, and that's all you have to know. You don't have to understand detailed rules about how subtyping works. We haven't completely achieved that because we're doing mutation 2, which is not a great fit for it, and we'll see that a bit later. So let's just dig in, and I'm just going to go through how the type system works and explain how types of sets of values works. Okay, so types are sets of values. What are values? So we start off with values, and we've got to have a universe of values, and we partition that universe into what we call basic types. You might call them sorts or something like that. So so to start off, we've got booleans and integers, and those are different things. We've got 64-bit integers, so that's 2 to the 64-bit signed integers, so it's 2 to the 64 values. Boolean's got 2 values. So the type boolean is a set with 2 values. The type int is a set with 2 to the 64 values, and we can combine them with OR. So boolean or int is a type that contains all the booleans and all the ints. We can give names to types, and there's no semantic to the name. It's like a type def. It's just it's exactly equivalent to the left-hand side. Is exactly equivalent to the right-hand side. So how do you actually, if you've got a union, how do you actually do something with it? And the way we do something with it is with the is operator, and so it's kind of JavaScripty. Kotlin actually, I think, has exactly the syntax. So if we've got a type bi that is either a boolean or int, we can test if it's an int, and if it is, we return it. And then if it's not an int, then it must be a boolean. So let me just see. I think I got a little pointer thing I can use. Just figure out how I do that. Okay, I think I can do. Yeah, can you see? Can you see a pointer? Okay, so here we've got a type boolean or int. Here we're testing if v is an int. So what's interesting is we narrow the type of v from being boolean or int. We've now narrowed it. So within this scope, v is now an int. So when we return v here, and we've got a return value of int, that's okay. Since v here is int, we now can narrow the type here to boolean. So v here is a boolean, which means it's okay to use it with if. And this is something in the Kotlin and TypeScript both have. Okay, so another interesting, so next stage, so that's very straightforward. So we can also have singletons. So a singleton is a type that denotes a set with a single member. So we can have a type 1, which just contains a single value 1. Now, usually when you have a type that's a singleton, it's more convenient to use a const to define it. And what a const does is it gives you a name for a value, and that name can be used within a type descriptor to denote a singleton type, and it can be used within an expression to denote a value. So here we've got constants RGB, and we're using it within a type. So we're having a type that's a union of 3 singletons and giving that a name. And here we're using, so this is using the const as a type descriptor. And here we're using the const as an expression to denote that value. So we've got a variable of type RGB, which means it's got to be 0, 1, or 2, and we're initializing it to that value. And if you think about Boolean, actually we could define our own. So T is exactly equivalent to false. So we have, the language has built-in true and false keywords, but we could define our own if we liked. We could define T to be true and F to be false, and we could define a type Boolean to be true or false, and this would be exactly the same as our Boolean type. So it's just a set of values. So we have a nil type, which contains a single value, and we do optionality just as union with nil. And functions that don't explicitly return a value return nil. So if I don't have the returns bit, here, that means returns nil. And if you fall off the end, I should have an example. If you fall off the end, then that returns nil also. And we can do type narrowing when you do an equals equals, that also type narrows. So here I've tested whether v is nil. So here I know v is not nil. So I've narrowed the type here from in question mark to int. So I can return it. I can return it here. If there's anything not clear, feel free. Since you've got a small group, do feel free to jump in and ask questions. And okay, so next type we got a string. So string is immutable. It's a sequence of Unicode code points, and we can have unions of these. So here's an operator, and it's a union of these strings. And in num we have an num syntax that is just sugar for a combination of, it avoids repeating yourself. So if I have a num with 3 values like that, that's exactly the same as defining 3 consts and a type that is the union of those 3 consts. We also have floating point values. We have 2 kinds of floating point. We have a float, which is 64-bit binary, and decimal, which is 1 to 8-bit decimal floating point, base 10 floating point. These are both IEEE 754 floating point. Now, the interesting thing here from a types perspective is that the IEEE semantics for decimal include precision. So 1.0D is a distinct decimal value. It's not the same value as 1.00D. They are equals equals. They are mathematically equal, so it defines an equality operator, and they're equal, but they are distinct values. So when we're thinking in terms of types, we actually are not, I've said types are sets of values, and that's not actually true. They are sets of what we call shapes, where a shape is an equivalence class that's defined by the equals equals relationship. So if I have a type 1, so I'm defining that singleton value 1, and it's a type, and I can assign both this value to it and this value to it, and these 2 values will be equals equals because they have the same shape, but they won't be identical. So if a treble equals, which does, is it exactly indistinguishable values, and we have a double equals, which are, is it the same shape, and that's an equivalence relation. So really, when we're dealing with our types, deal with not all the nitty-gritty details of values. They deal with an abstraction of values that we call shape. And actually, there's a similar issue with float 0, in that IEEE has distinct plus and positive and negative 0, and so we treat those as being the same shape, so they're equals equals, but they're not identical. And this shape versus value distinction will become more important later on. Okay, so let's get a little bit more interesting. So structures. So we have 2 kinds of structures. First one is list, which is an ordered list of values. And we have 2 ways of just 2 kinds of type descriptor for describing lists. So we have arrays. Oops. We have arrays, which looks like C arrays. So that's saying that every member of the list is of type int. And we also have tuples. So this is saying we've got a 2-tuple where the first member is a string and the second member is an int. And we're giving a name of that of location. And then we construct it. This is our value constructor. So it constructs the list. This is a type constructor. So the really important, so with tuples, you are giving a separate type for each member. With arrays, you are giving one type for every member. But what's important here is that there are two ways of describing the same thing. So this is not two different kinds of value. It's one kind of value, list, and we can describe lists in two different ways. You can describe it by saying, oh, it's a list with all members of this type, or we can say specifically what each member is. And so the way this works in expressions is we have a singleton type. So suppose we have a location which has a first member of string, second member of int. If we do an array access on that, our 0 is a singleton type, 0. So we know when we project, we do a projection of member type 0 for this, we're going to get a string, and when we do 1 here, we're going to get an int. But if we had a value here that was not a singleton type, it was an int, then the member type that we get would be the union of these. So this fits in with having one kind of thing here, fits in with Json, which doesn't have distinct array and doesn't have distinct array tuple concepts. It just has things in square brackets that it calls arrays, which can be used to represent tuples and can be used to represent arrays. And we also, you can actually have a ... on the end of you can have a type and then ... on the end of your tuple syntax. So actually tuples are strictly more general than arrays because you can write T with brackets as just a tuple, which allows any number of T's. So really array is just a shorthand syntax. So if you think about how typing on lists works, they're covariant, array and tuple types are covariant in the member types, which is kind of what if you think of these things as being sets of values, it's what you'd expect. If you've got a list of oranges, it's a list of oranges or apples. So suppose we have a type, just concretely, suppose we have a type that has 2 floats, and then we have a float or nil. So float's a subtype of float question mark. So coord is a subtype of opcoord. And similarly, a tuple is then going to be a subtype of, so if you've got a location that's a tuple, that's going to be a subtype of an array of string or ints. This is perhaps a little bit less obvious, but if you've got a tuple whose first member is int or string and whose second member is int or string, that's actually equivalent to a union of 4 things. You can either have, the possibilities if you've got int or string is int, string, int, string, or string, int. So these actually are equivalent, and the type checker actually has to recognize that these are semantically equivalent. And actually recognizing this kind of, that these things are equivalent is really the basis for how the type checking algorithm, works. So we got two fundamental kinds of structure. We've got lists and we've also got mappings. We use the word mapping because just as we have lists, we have 2 ways of describing them, arrays and tuples. So with mappings, we have 2 ways of describing them. We have a map where you are describing, you're giving one type for every member. Or you can have a record where you give a separate type for each member. So here we've given a name to a person, and then we've got a nested record type here. So person is a record who's with one member, who's with two members. The first member has a field name and his type is a record, and the second member of person is has a integer field ID. So note that our syntax for, so here actually you can put these in literals if you like. So that is, so our expression syntax for values is a superset of JSON. So you can put JSON syntax in here and it just works. And again, records and maps are two ways of describing the same thing. And that corresponds to JSON, which just has a single syntax for this kind of thing, which is object. And that is used both for objects that are conceptually representing maps and for objects that are conceptually representing records. The reason why we have this kind of delimiter curly vertical bar will become evident in a minute. So we also have optional fields. So this is a record where we're saying you must have a name field, and you may or may not have a year of birth field and country of residence. And here we are constructing a record which has one of these optional fields, but not both. So this is critical when you're wanting to describe data on the wire. Most JSON out there has a ton of optional fields, but it's not something you typically see. Well, no, maybe it doesn't come in a lot of languages, but it's basic in when you're using any sort of schema language. It's a pretty fundamental capability. So we also have, just as with tuples, we have a ... thing where you can extend it. We also have that with records. So you can say that you can have a record where you have a name field and a string name field, an int ID field, and any other kind of fields you want, but they've got to be a type string. So an example would be here, we have another field, preferred beverage, with value coffee, and that's okay because I've said it's allowed there. And we require you to use JSON syntax here, because otherwise there's a potential, if you have an optional field and you spell it wrong and you have an open thing like this, then there's a potential for it being, it's very easy to make typos. So we've just, to make it clear that you are really wanting to have one here and you didn't just misspell an optional field here, we require you to use double quotes here. And just as in fact, arrays are really a special case of tuples, so maps are a special case of records. So T1 and T1 can be equivalently written as T2. So that, I think we have quite a pleasing, it's quite a pleasing symmetry, I think, between lists and mappings, two ways of describing. So you have lists where the keys are ints, you have mappings where the keys are strings, and in each case you have two kinds of type descriptor, arrays and tuples, and maps and records. So I think there's quite a nice symmetry there. Or at least I like it. So types can be recursive. This gets a little bit more interesting. So we could have a linked list type where you have a recursive reference. And not all recursive references, so another example of this, which we use all the time, is JSON. So our JSON type is either nil, so we allow nil to be written as null, if it's a Boolean, or it's a number, or a string, or it's an array of JSON values, or it's a map of JSON values. So not all recursion makes sense. It doesn't make sense, for example, to have something like this, bad is int or bad. And the rule is that when you have a recursive reference, that recursion must traverse a constructor like a record or a map. So it's inside, this is okay here, this recursive reference, because it's inside a record. Similarly, if it's inside a record or a map or a tuple, that would be okay. If it was outside like this, that doesn't work. So we also have another important type in addition to JSON is any data, what we call any data. And any data represents what's called in some languages plain old data. So it's data that's designed to be independent of any program. It's data that you can send between different programs on the network without any pre-negotiation. And for the any data type, the equals operator is well defined. So it's data that you can serialize and get it back and get the same thing. Equals, double equals, deep equality is well defined for it. And any data is basically JSON plus tables plus XML. So it's basically the same definition, except we're recursorily referring to any data here, and we're adding XML and we're adding table. I'm not going to go into too many details about XML, but it's basically a sequence type. So just as a string is a sequence of characters, so XML is a sequence of elements or processing instruction or comments or text. It's a similar model to XQuery. Table is similar to an array of records, but it has the functionality of being able to look up things by key. And I'll come back to records in a bit. And now we can actually explain our regular record syntax actually uses curly braces instead of without the vertical bar. And that is shorthand for being open to any data. So our records are by default, the normal record syntax is open. It means you must have at least that. You can have other stuff if you want it, but it's got to be data. So this means this is convenient for having extensible schemas. When you want to have an extensible schema on the wire, you can use this record type works well. So as well as any data, we have a bunch of stuff that's not data. So data is our key kind of, we're a kind of data centric. We can think of Ballerina as being a data centric language. We also have a bunch of types that aren't any data. So we have a distinct kind of error type. And in Ballerina, error handling is based on returning error values in a kind of not dissimilar way to Go. But we actually have a distinct basic type, so that the language can treat errors. We can have distinct rules in the language for dealing with errors. We also have functions. We have objects that are fields and methods, and that builds on function. We have a type dest type, which is a runtime type. We have futures, which represents a separate thread of execution. We have handles that are used for foreign functions, and these are all the error function object type dest future handle. They're all basic types. And we also have an any type, which is basically everything other than error, which is perhaps confusing, but we want it to be explicit. One philosophy in Ballerina is you want to be explicit about errors. And so if you want a function to return an error, you say something or error. You can have error subtypes too, but so we have the any type. I'm not going to go into huge detail on any of these, but I will talk a little bit about objects. So objects, the typing works in a uniform way. So an object type is really like it's kind of like an interface. It gives you the types of the methods and the fields, but the object type doesn't tell you anything about the implementation. Typically, the way you create an object is you define a class, and the class both defines a type and an implementation of the type. So here we've defined a class integer, and that defines a class that we can use in new, and it also defines a type, and that type integer is a subtype of incrementable. So we can assign an integer object that we just created to incrementable. And we also have object expressions, which just create an anonymous object too. And Ballerina isn't an object-oriented language, but objects are important. In particular, objects are used to describe the network interfaces. So each network, ingoing or outgoing network interface, is described as an object type. So we have service objects that describe services that describe the services that a program provides by describing an object, and you can consume network services using client objects. And then the types of the methods on the service and client objects are the types I've been talking about, which describe the format of network messages. So that's how it all kind of fits together. We also have something we call distinct types, which is similar to branded in modular 3. I think it's quite often called branding. So basically, it's adding the functionality of nominal types to a structural typing framework. So if I didn't have the distinct keyword here, X and Y would be exactly the same type. But by saying distinct here, I'm creating a unique brand, a unique type ID. And when I create a value of type X, it will be tagged with a distinct ID, which distinguishes it from things that have the same structure. So sometimes when you're dealing with objects that are going to be used within a program, you don't want structural typing, you want something that works a bit more nominally, and distinct types do that. And so we provide distinct types. So it's not when you've got distinct types, then you're not any data anymore, because your distinct types are tagged with your module ID with a particular part of the program. So we provide distinct types purely with the non-any data types. Specifically, we provide them for objects, and we provide them for errors. Often when you're dealing with errors, you want to associate them with a particular module, particular name, and we do that by declaring the errors as distinct. So now I want to get on to mutation, which is where things start to get a little bit more complicated. So when you have mutation, it means your values have an identity, right? So you can't think of a list as just being its members. There's a specific identity to it. If I just, this is obvious stuff, but let's just go through it. So if you create an array of one element and assign it to X, and then you assign X to Y, these are both referring to the same thing. So they're both, X and Y are both double equals and treble equals. If I create a new array, then it's double equals, it's deeply equal. So in Lisp terms, it's equal, but it's not eq in Lisp terms. And when we change something, then this is going to change. So that's the identity is tied to mutation. Being treble equals means you mutate one thing, and it will also mutate the things that are treble equal to it. So that will mutate Y, but it won't mutate Z. So this means we can't really think, once we have mutation, we can't think of types as being sets of values, because our values, there's more to values than just the members. There's this identity. So this goes back to the shape idea I was talking before. We now have to think of types as dealing with an abstraction of values. So the abstraction of values that we're dealing with here is one that ignores mutation. So we don't care where it's stored. When you give the type of something, you're just talking about its shape. You're just saying what are its members. You're not saying anything about its storage location, and the type doesn't tell you anything about the graph structure. When you describe the type of something using the type descriptors I've shown you, you're thinking of the value as being a tree, and you're describing what that tree looks like. You're not thinking that there may be a graph there, but the type tells you nothing about the graph structure. So when we think of a type as being a set of shapes, our shape for a list, a shape for structures is really a tree. And if we have so if we have something like this, so we have this LL value here, that has a cycle in it, right? So I've created a value with a cycle. And if we ask, just by mutating it, I've got something that points to itself. And if you ask what the shape of that is, well, you unfold it as a tree, and it's basically an infinite tree. Oops, I've got a little typo there. So basically, types are dealing with not with value. Types aren't sets of values; they're sets of shapes, and which are an abstraction of values. And the abstraction of values that they are is when you apply it to lists or records, they are trees that can be infinite. That's the first complication. Second complication is we have a bit of a problem because of aliasing. The combination of aliasing and mutation and covariance gives us a problem. Okay, so how does this work? So imagine, let's first of all, step one, let's create a list. Let's say an array of strings, and we're going to assign it to another variable that is an array of either possibly null strings. That's okay because of covariance. Now, suppose we so first member of that was a string. Now, suppose we assign nil to the first member via this alias, and then we access it via the original one. We've got a problem. So somewhere this has got to fail. This can't work, right? So we've got a problem. And it's the same problem that Java arrays have a similar problem. And the way we solve this, our solution to this problem is to say that a mutable value, has what we call an inherent type. And what the inherent type does is constrains how the value can be mutated. And this constraint is enforced, well, it's enforced partly at compile time, but ultimately at runtime. So we're trading off here to keep things simple. And you could have a more complex type system where you express the variance of types and so on. You could do that in the type system, but that would not fit our target audience, where we were trying to keep something that's already at the type system is already at the kind of limit of what's supportable by our target audience. So we made this trade-off that some things would be only enforced at runtime. So I think a type theorist would call this unsound. That seems, I always think that's a little bit of a judgmental word. The way I like to think of it is that what does the type system guarantees? Well, the type system guarantees that if you have a variable v of type whatever, so you have a variable v of type int, what we guarantee is that if you get a member and you read a member from v, we'll have type int. What we don't guarantee is what will happen if you try to store a member there. If you try to mutate it, it may work, it may not work. We don't provide any guarantees about that. But we do provide an absolutely cast iron guarantee that reads will work. And this is not dissimilar to how Java arrays work. If you do the similar kind of thing here in Java, you will get a array store exception, I think. So just applying this to our example, here when we construct a list, the context, the type context here, we're saying we expect, in this context, we know we are expecting an array of strings. And that means that when we construct this list, we construct this list with an inherent type of array of string. So that's part of the runtime value. It has a type saying, this is an array of strings. If we try to do this, it would be a compile time error because you're assigning nil to something that's an array of strings. This is okay. So here we've assigned it to this. This is still okay. So now we have a variable v2 that has a compile time type of array of optional string, but its inherent type is array of string. When we try now to mutate this thing we created here via this will get us a runtime error. And this array will say, oh, sorry, you can't do this. My inherent type is array of string, and you're trying to mutate this value to nil, and that's not allowed. So this will throw you, this will give a runtime panic.
A quick question here.
Yeah, sure, absolutely, great.
Yeah, you kind of answered it, but when you said it's a panic, so it presents a, it doesn't go through the normal error mechanism of returning a value. It's
no, that's quite right. So we have two,
absolutely.
Two so we have two kinds of, it's kind of like Go, we have two kinds of errors. We have kind of expected normal errors, which go through the returning an error. And then we have panics, which are basically things, it's somewhat like Go, somewhat like Rust. I think Rust has a similar distinction. It's things that something's gone wrong, basically. And we call those panics. And I guess they are really exceptions, but the expectation is you're not going to catch these things in most cases, and there's not much you can do about them.
Yeah, they're almost guaranteed bugs, right?
Yeah, basically bugs, resource exhaustion or bug, basically.
Yeah.
And we call those panics.
That makes sense. Thanks.
Okay. So we've got this inherent type, and this is not a good thing. This is not a good thing. This is a necessary evil that is required in order to be able to have, we want two things. We want structural typing with semantic subtyping, and we want mutation. And those things really don't go terribly well together, but we want them both, and we're going to have them. And the way we get them both is by having this concept of inherent type. But it complicates things. And so now I'm going to talk about, well, how do we deal with all these? It creates a whole bunch of complications, which we now have to deal with. And so I'm going to try and explain how we deal with the various things various complications that this creates. So first of all, we got two relationships between a value and a type. So the words we use for this are looks like and belongs. So the kind of more regular one is, okay, so a value looks like a type if its shape is a member of the set of types denoted by T. So that's the normal thing. It's got, you've got an array of ints and your value is currently 1, 2. Okay, you look like that type. But there's another relationship, which is the one we actually have to use, which is, what happens if you mutate it? So in order to say that, when I say V is a type int array of int, what we need for that to work is, no matter how you mutate V, its shape will belong to array of int. So that means its inherent type has to be a subtype of array of int. Anyway, so we've got two distinct. I'll come back to that in a bit. We've got two distinct relationships. Does it currently look like something, and versus no matter how we mutate it, what could it look like if we mutate it? We've got two slightly different things we have to distinguish: what it currently looks like and what it could possibly look like. So our is relationship is dealing with, when you're doing types, we're looking at what it could possibly look like when you mutate it. But sometimes you want to know, what does it currently look like? In particular, if you're bringing stuff on the wire, it comes in as JSON, it can be mutated any way you like. So what we want to look at is, what does it currently look like? So we can't use is for that. That's not going to work. And so instead we have a separate statement for this, a match statement, which looks at its current value and matches that. We have patterns which look a bit like types, and we are matching that against its current shape, and we're not paying any attention to its inherent type. So this is basically like a kind of a switch statement on steroids. Again, this is not, so we have type match, which considers how the value could be mutated, and we have value match, which just looks at its current value. So another problem is if we didn't have mutation and we didn't have inherent types, suppose we get a value in over the wire as JSON, and we want to convert it to some user-defined type. So suppose we have a point something, some user-defined type, float x, float y. We want so when the user writes code to handle incoming data, they want to manipulate it as type data. They don't want to manipulate it as JSON. We want to turn it into nicely typed data so that the user's program is nicely type checked. If we didn't have inherent types, we could just simply cast from JSON to the type, and that would work. But because of inherent types, we can't do that. If we try to, if we've got a value here like this, and we try to just cast it to point, it would say, sorry, you can't do that. And it would say, sorry, you can't do that because the inherent type allows JSON to be mutated to be something that isn't a point. So we can no longer simply do a cast. And instead, we have to have a special language feature for this, which we do via a built-in function. We call it a langlib function. So this involves a whole bunch of machinery here. So first of all, we have a type desc type. So we have one of our basic types is type desc, which describes the type. The type parameter says what the so if I say type desc any data, that means it must be a type that is a subtype of any data. And we have this T here also occurring here, which is, you guys were talking about dependent types, so you know way more about this than I do. But this is a very ad hoc, a very sort of ad hoc limited version of dependent typing. We're saying that the type you pass in here, the value you get will depend on the value of this argument. So if I pass in and this says we're defaulting it. So if I pass in a point here, this is implicitly passing in a point type desc here, and it's saying that we get back something that is equal, whose type is equal to the value of that argument. So it's we don't have this in a general form. We'd like to add it more generally, but this is a rather kind of very sort of ad hoc limited form of dependent typing. And this thing says we basically do a little, it's basically you default this from the context, but there's a little bit of unification going on also. And mostly the user doesn't actually have to do this. The user just declares the parameters or return type of their method as being whatever they want, and the language framework, the network interfaces take care of converting it from the wire format to the user-defined types. But under the surface, it's using this feature, and this is basically doing a it's basically recursively constructing the type from the data. And this is complexity that comes partly from having inherent types, but actually it also comes from having numeric types. So JSON just has one numeric type, float. We have 3. So another awkward thing we have to deal with is converting from what's JSON numeric format, single numeric format on the wire, into R formats. And this also, from JSON with type, also deals with that. Sorry. So the next thing I want to talk about is we've had mutability. We also have a way of saying that something isn't mutable, and this is our read-only type, which I think is I want to go into depth in because I think it's quite interesting. So what read-only does for us, it does really does three things for us. It's the foundation on which we build the concurrency safety features of the language. It reduces the bad stuff, some of the bad stuff we've seen from inherent types, and it enables our table data type. And we want to do this without complicating the language for beginners. So we don't want something where this shows up in a beginner's use of the language. So as always in Ballerina, you start with a value and then go on to the type. So the foundation of having the read-only type is to have values that can be immutable. So structural values, that's lists and mappings, they can be constructed as immutable. And once they've been, so what does immutable mean? It means once you've constructed it, it cannot be mutated. You can't change it. And a key feature of our immutability is that it's deep. So if you have an immutable list or an immutable mapping, then all of its members also have to be immutable. And some basic types are always immutable. So, you know, our simple types, strings, errors, functions, they're always immutable. And the big thing about, so remember that inherent type was there to constrain the range of mutability of a structure. If structure can't be mutated, then they don't need inherent types. So for immutable structures, we don't have the complexity of having two relationships between a value and a type. We just have, you know, you don't have to worry about how it's going to mutate. It is what it is. It can't change. So that, you know, structural typing, semantic subtyping can just work in a straightforward way without all the hacks that we need with inherent typing. But to make that work, we actually have to bring this concept of immutability into the type system. So we do that with a type by adding a type read-only. And that combines with intersection typing. So read-only by itself means that the value is immutable. So a value belongs to read-only type only if it's an immutable value. So if I have a type like, suppose I want to have an immutable array of ints, what I say is that it's an array of ints and it's read-only. So when I do this, when I say that my context, when I have, and I say the type I'm expecting is a read-only array of ints, read-only is a read-only structure, this thing here will then construct an immutable value. And you can put the read-only in a type definition. So here we're defining a type that is a read-only record. And then when I construct that value, it will be constructed as immutable. So, you know, a library, somebody who's writing a library, they just put read-only in, and the user just doesn't have to worry about it. So it's important to understand that read-only confuses people because it's different from the way things work in other languages. So in particular, read-only NT is a subtype of T. So that's, I mean, the syntax suggests that, right? If it's both read-only and T, then that is a subtype of T. But that implies that when you say something, when you don't put read-only in the type, so if I'm just saying array of any, that doesn't mean it's mutable. That doesn't mean mutable array of any. It means it's an array of any, and I'm not saying anything about mutability. And that means that if you try to store to a member of a mutable structure, that may not be detected until runtime. So that's a similar situation that we saw with inherent types. Sometimes you will detect that at compile time, but sometimes it'll only be detected at runtime. And that's the same with immutability. And that's very different from how things work, like something in C. So they're doing a different thing. So if I have, suppose in C, I have a parameter type, const t star, right? What that is saying is it's constraining, it's telling the callee, you are not allowed to mutate stuff via that pointer. The read-only is working the other way around. Read-only in Ballerina, if I say a parameter is read-only t, it's saying that the caller must provide an immutable value. So it's a constraint on the caller. They have to do something extra, not a constraint on the callee. So it's not the same thing as constant T star, and it's trying to solve a different problem. And the problem we're trying to solve with read-only is concurrency. So when you have a value being declared as read-only, you are absolutely guaranteed that it can never ever be mutated by anybody, any thread, anytime, anyhow. And you're also guaranteed that because of the deepness, you're guaranteed that nothing reachable via that value can be mutated. So that means that if you have a variable that's type read-only, you know that it's safe to pass that value to a function that's running on a separate thread. Or to put it a slightly different way around, if you've got something that's a function that is running on a separate thread of control, if the data it's sharing is read-only, you can go run that function in parallel on a separate thread. It's safe to run it on a separate thread. So it's not enough. So read-only is designed for concurrency. It doesn't solve concurrency safety on its own. There's a whole lot of other stuff that goes with it, but it's the basis on which we can add features that provide us with some concurrency safety. What we're trying to achieve with concurrency safety is to determine when it's safe to run a function on a separate thread. So our threading model, we don't have async functions. Instead, we have basically you write things. We have what we might call green threads. We call them strands. And when you run something on a separate strand, you're not saying whether it's running in parallel or not. You're saying it's logically it can be run using cooperative multitasking. And then it's up to the system to figure out, is it actually safe to run that thing in parallel or not? And so it's a job. So the user has to, the system has to look at the types of the functions and how they're used, and figure out, can we run this in parallel or not? And it's actually crucial to be able to run things in parallel, because we're writing services, and these services need to be able, you've got to be able to service incoming requests in parallel to get reasonable performance. And so what we're trying to do with concurrency safety basically is figure out, when is it safe to run functions in parallel? So one part of this is having data, being able to declare data as immutable, because that is inherently something that can be shared between functions running, that is safe for functions running on separate threads to share. But we also need a bit more than that. So the concept we have is called isolated. So a function that's isolated, it's only allowed to access mutable data through its parameters. It's quite similar to a pure function, but it's not as strong. So I think something like D, for example, has pure functions, and this is not dissimilar. But pure functions are they're too constrained to be useful. Pure functions can't have any side effects at all, and that doesn't work for us. So instead, we have a weaker constraint that they can't go access global data, mutable global. They can access read-only global data, and they can also access their parameters. So if you pass them mutable data in a parameter, it can go access it. But it means by saying they access mutable data only through the parameters, the caller can make them safe. If the caller then passes in any parameters that are not shared, then it can ensure that it's safe to run the function in parallel. And the way I think of it is that isolated for functions complements read-only for data. So functions are always read-only. You can't mutate code. We don't, I mean, you can, but we don't allow it. But a function being read-only tells you nothing very interesting about the function. What you want to know is what happens when you call the function. How will that affect mutable data? And that is what isolated does. So isolated gives you some constraints about when you call this function, what can it, how can it mutate data? And you can, the reason it's isolated is it's by saying that it will only access mutable data through parameters that you provided. You can constrain it not to access mutable data by providing it with appropriate parameters. We also need, we also have isolated objects. And the idea of isolated objects is that they can have mutable state, but they encapsulate that mutable state, and they don't allow that state to be accessed from outside. And we also have compile time rules that ensure that appropriate locking, that the object itself appropriately locks all of its mutable state. So from out, it's safe to pass isolated objects to isolated functions. Now this is all pretty complicated. I could give a whole talk about this. This is all pretty complicated. And basically, to make this usable for our target audience, we can do a lot of inference. So basically, the user writes stuff, and then the compiler figures out that things are isolated. And it can also tell them that in order to run this stuff in parallel, you need to add. So we have a lock statement, and we tell us that it can. I'm not sure it's implemented yet, but the idea is that it will. It can guide the user and tell them where they need to add locks in order to be able to have this stuff run in parallel. Okay, so this is another problem that we have with inherent types that read-only alleviates. So let me walk you through this one. So suppose we have a type n, which is a one tuple that's an int, and we have a type s that's a one tuple that's a string, and we have another type ns that's one tuple of either int or string, and we have a function that takes an n or s, and so we're going to test whether it's n, and if it's an int, we can access the first element, which will give us an int, and then go to string. Now you might think, and in fact I did think for a while before I figured it out, that it was safe to narrow x to s here. So this is n or s, right? So this is an n, so we can just make x be s here, right? You might think. But this doesn't actually work. And the reason this doesn't work, and this actually has to be a compile time error. Why does it have to be a compile time error? Well, consider we have a function g here. So we're going to declare this value x as being type this, and we're going to create this value. So it's an int, and it has this inherent type. This line here is going to fail because this, with this inherent type, so for this line to succeed, this line cannot succeed because this value could be mutated so that it wasn't an int. So because of inherent types, the test that we do here is the inherent type of this value a subtype of int? And the inherent type of this is int or string, which is not a subtype of int. So this line has to fail. So this line would succeed, but obviously this would give the wrong answer. So it cannot work. And the reason it can't work is, what do we know here? All that we know here is that the inherent type of x, so we know that the inherent type of x belongs to this set, the union of this set and this set. And we know that the inherent type of x is not a subset of this. We cannot infer from that it is a subset of S. So it just, if we write this down with a bit of symbols here. So if we write X for the inherent type of capital X for the inherent type of X, So we know here that this is saying that X, the inherent type of X, is that set is a subset of this. And we know from here that this is not a subset of this. And that does not imply, if this was going to narrow to string, it would have to imply that X was a subtype of S. But that's just not, you know, that in set theory, that's not true, right? Because, am I making sense? That just doesn't work. So unfortunately, this cannot work because of the inherent types. You would expect this to be narrowed to S there, but it can't narrow to S. So this is not good, right? Let's be clear. This is not great. But it's kind of, I think, an unavoidable consequence of a combination of subtyping, semantic subtyping, and mutability. That's the bad news. The good news is we can actually get everything to work properly with read-only. So if I declare these types as all these types, so all I do is change these types here to be read-only, this can all work properly now. And the reason this will work properly is if I pass in X here, this will succeed because we're not looking at the inherent type here. If I pass this in, this value, which is, you know, it's a list of one int, so this will be true. We don't have to worry about inherent type nonsense. We're just saying, is it shape an array of ints? Yes, it is. So this is true. So everything works nicely. So basically, with read only, we can regain what we've lost. Well, basically, you pay for mutability only when you need to. When you can use read only types, the type system can work in a nice, clean way. When you have mutability, then you have some hacks well, I wouldn't call them hacks. You have compromises. You have necessary compromises, but you can get rid of those compromises when you have read only. So the final thing that read only does for us is it helps us with the table type. So the idea of the table type is it's like an array of records, but it has basically a primary key-like feature. So this is saying that the symtab type is a table that contains records of type sim, and they are uniquely identified within the table by the value of their name field. So the table maintains the invariant that the key uniquely identifies the records within the value. You're going to have the keys spread out multiple fields. You're not restricted to having a simple type. You can have an arbitrary structure here. You could have a name or whatever, anything that's any data, anything that you can compare for equality, you can have here. But it has to be read-only, because if it wasn't read-only, you can have an alias to it that mutated it, and that would defeat the ability of tables to maintain that invariant. So we have to insist that the key field, both the field itself and the value that the field contains, have to be immutable to enable the table type to maintain this invariant. And this table type is really key to, so I mean, languages divide into languages that basically provide a rich set of they provide built-in collection types that they expect you to use. So Lisp, Python, JavaScript, or languages that kind of where the expectation is that you're going to roll your own, you're going to have your own special collection types for things. They're not built into the language at all. So Ballerina's philosophy is very much that collection types are built into the language. They're part of the language. You use them as much as possible. But if we only had lists and maps having, with keys or strings is just not enough. If you want to write a sophisticated application, and any kind of associative, any kind of hash table you can have is something where the keys are string, it requires an enormous amount of hacks to do anything sophisticated. Whereas this type actually is powerful enough that you can you can write sophisticated applications in Ballerina without having to roll your own collections. And it also works well with some other things that we have. Ballerina has language integrated query and a variety of other things. And this table type works quite nicely with that. And that depends on read only to work. Okay, so that's my overview of the type system. We could talk a little bit about how you actually implement the subtyping algorithm. So there's a paper. You guys like obscure papers, so this is the key paper here by George, I think it's Castagna, who's a professor in France, and he's one of the people behind CJuice. And this is a great paper. He's written a bunch of papers over the years. There was one which is called Gentle Introduction to Semantic Subtyping, which I found completely incomprehensible. But this one actually is quite easy to understand. It has actual algorithms and stuff, and so this is what we've used to implement it. So the basic idea in the basic idea in the algorithm is, if you want to, so we got these two type descriptors, which can be arbitrary, complex, and recursive, and we've got to find whether one's a subtype of the other. So the first step is that when you want to test whether S is a subtype of T, what you do is you take the difference of S and T, and then you see whether it's empty. To test whether something is empty, we split it up into what we call uniform types. So uniform types are like basic types. So remember, we had int and string and error and list. So basically, you split up your types into these separate, and also these basic types that are partitioned. Since they're a partition of the value space, we can split it up into, so we split a type out and say, okay, so what is allowed from int, what is allowed from error, what is allowed from list, what is allowed from mapping. And if all of these are empty, then the type is empty. So the first step is we split this up into basic types, and then we test whether each basic type is empty. And we handle read-only by treating a read-only as by splitting something like list, which is can be either read-only or not read-only. We split it into two. So we have basically mutable lists and read-only lists, and we check. What we're doing is we take this type, we split it up into uniform types, and we test whether each uniform type is empty. And then each uniform type has a specific representation for its subtype. So ints, for example, we represent as being ranges, because we have subtypes of int for byte, for example. Byte we represent as being a range from just byte in our worldview is basically 0 or 1 or 2 or up to 255. Int 32 is just, it's just a subtype of int. So the way we represent ints is as ranges, and then you need to be able to form union intersection difference on those, which is easy to do with ranges. For structures, the way you represent these types is with a kind of binary decision diagram. So it's so basically you put it into disjunctive normal form, where your atoms are the record type descriptors or tuple type descriptors. And then the way you figure whether something is empty is you're basically doing a search for where it can be non-empty. That's my short summary. A long summary would be going through the algorithms. It's a very worthwhile paper to go through that one, but it's quite complicated. So where's this at? So we've got a current generation product which we call JBallerina, which is written in Java and compiles to JVM bytecode. And this was started a long time ago before I even got involved with it, I think, and it's evolved from when the type system was very different, and it's not quite doing semantic subtyping according to the spec. It's kind of a syntactic approximation. And we're also doing a kind of next generation product, which is a next generation implementation, which is written in Ballerina. So we have a Ballerina compile written in Ballerina, and we're bootstrapping with JBallerina, and we compile to LLVM. And our initial focus there is getting the semantic subtyping working properly. But it's going to be quite a few years before that's ready to replace Ballerina. But we're planning, in the meantime, we're going to backport the semantic typing so that we have type system properly implemented before Ballerina is ready. In terms of future stuff we want to do, we don't have generics yet. We know we want to do generics, but I also know they're hard. It's kind of scary. We also want to be able to have refinement types. So we want to be able to say that it's something's a string that matches a regular expression. Basically, we want to be able to have arbitrary expressions to constrain the to further constrain the set of values, but probably not to implement that. But probably that's only going to be enforced at particular times. And then at the moment we have and on or. We also probably going to want to add not. So in terms of further information, there's the Ballerina website, which is ballerina.io. And then there's this really good paper. And if you actually want to see an implementation of, you want to see what I think the biggest Ballerina program in Ballerina is this thing, which is our work in progress compiler, which is written in Ballerina and does a good chunk of semantic subtyping. So that's on GitHub. That's my current project.